welcome. Thanks for joining me. The message you sent 5 minutes ago. Somewhere, right now, a server is quietly copying encrypted internet traffic and storing it. Not because anyone can read it today, but because someone is confident they'll be able to read it eventually. This is not a speculation. It is a documented named threat model, and intelligence agencies openly acknowledge it as already underway. It has a name in the cryptographic community: harvest now, decrypt later. And it means that data encrypted today, medical records, defense communications, your own private correspondence, may already be sitting in someone else's archive, waiting for a key that doesn't exist yet. What a quantum computer actually breaks. Nearly all secure communication on the internet, HTTPS, VPNs, banking transactions, digital signatures, relies on a family of encryption methods: RSA, Diffie-Hellman, and elliptic curve cryptography. Their security rests on a simple engineering fact. Certain mathematical problems, like factoring enormous numbers, take an ordinary computer an impractically long time to solve. A sufficiently powerful quantum computer changes that math entirely. Using an algorithm developed by mathematician Peter Shor in 1994, a large enough quantum machine could solve those same problems efficiently, rendering the encryption that protects most of the modern world computationally worthless. This isn't theoretical parlor trick. It's the reason cryptographers, intelligence agencies, and standard bodies have spent the past decade preparing for a single hypothetical data they call Q-Day. Harvest now, decrypt later. Today's threat, not tomorrow's. Here is what makes this urgent rather than academic. You don't need a working quantum computer today to start exploiting this vulnerability today. You only need patience. Sophisticated, well-resourced actors, the kind capable of large-scale data interception, can record encrypted traffic now, store it, and simply wait for data with a short shelf life. This is irrelevant, but for data that needs to stay confidential for 10, 20, or 30 years, government sectors, government secrets, long-term medical records, intellectual property, infrastructure design, the clock is already running. If a capable quantum computer arrives at any point during that confidentiality window, everything harvested along the way becomes retroactively exposed. Analysts applying this framework estimate that the overwhelming majority of healthcare records are classified government data encrypted today would qualify as vulnerable under exactly this scenario. How close are we really? Estimates of the hardware threshold have moved considerably. Breaking RSA 2048 encryption is now estimated to require on the order of 1 million high-quality logical qubits, a substantial drop from earlier estimates, following research advances in 2025. For context, the largest quantum processors publicly deployed in 2026 operate with roughly 1,000 noisy qubits. Powerful research investments in institutions and instruments, but still several orders of magnitude short of what's required. Cryptographers use a simple risk framework known as Mosca's Theorem to reason about this gap. Compare how long your data must stay secret against how long migration to new encryption takes, against your best estimate of when a capable quantum computer will arrive. Most serious technical estimates place that arrival sometime between 2030 and 2037, a range not a certainty, but close enough that any data requiring decades of confidentiality is already inside the danger window today. The defense NIST already built. The encouraging half of this story, the defense already exists, and it isn't experimental. In August 2024, following a public multi-year international competition, the U.S. National Institute of Standards and Technology finalized the first 3 post-quantum cryptography standards, ML KEM for encrypting data in transit, MLDSA for digital signatures, and SLH and DSA as structurally different, hash-based backup signature scheme. These algorithms runs on completely ordinary computers, no quantum hardware required on the defending side, and rely on mathematical problems that, as far as current research shows, resist attack from both classical and quantum computers alike. The United States has since mandated migration for federal systems by 2035, and major infrastructure providers, cloud platforms, browsers, messaging systems have already begun rolling those standards into production. What organizations should be doing right now? The practical guidance from the cryptography and standards community is consistent, and it applies well beyond governments and banks. First, inventory. Most organizations don't actually know where and how they use vulnerable encryption across their systems. That audit has to come first. Second, prioritized by data lifetime, not by system importance. A record that needs to stay confidential for 25 years is a higher near-term priority than a system holding data that's worthless in 6 months. Regardless of how critical that system otherwise seems. Third, begin migration now, deliberately and in phases, rather than waiting for a fixed deadline, because migrating an organization's entire cryptographic infrastructure is a multi-year engineering project in its own right, not a weekend patch. This is, as its core, a resource allocated and risk managed problem before it's a cryptographic problem. Precisely the kind of structured, deadline-aware planning that any well-run technical organization already knows how to expose and how to execute, applied to a genuinely novel threat. We are used to thinking of cybersecurity threats as things that happen to us in the moment, a breach, an intrusion, an attack with a clear before and after. Q-Day is different. It is a threat with 2 separate moments, the quiet theft happening today and the exposure that only becomes real years from now. That gap is exactly what makes this whole cycle a very dangerous one, and exactly why the organizations that act during the quiet years will be the ones that stay protected when the clock runs out. Thank you so much for your presence. Tell me what you think in the comments. Make sure I'll read them all.